Today's topic is rotational Raman spectra. First, we will see what is Raman effect. When a beam of light is passed through a transparent substance, a small amount of the radiation energy is scattered. If we consider monochromatic beam of light, a light of a particular frequency, then in scattered radiation we have components of incident frequency and components of greater or lower than that of incident frequency. Components of lower frequency gives Stokes lines and components of higher frequency gives anti-Stokes lines. These components of higher and lower frequencies are due to interaction of photons with the molecule. This photon can give energy to molecule or it can get energy from molecule. This is possible when molecule can have some rotation or vibration. So it have some rotational energy levels or vibrational energy levels. Now we consider pure rotational Raman spectra. In pure rotational Raman spectra, we consider two cases. First is for linear molecules and second is for symmetric top molecules. For linear molecules, the rotational energy levels are given by this relation Ej equal to Bj plus 1 minus Dj square j plus 1 whole square. Unit of this energy is written as centimeter inverse. It means that it is in units of wave number. So rotational energy in units of wave number is given by this formula Bj plus 1 minus Dj square j plus 1 whole square. In Raman spectroscopy, we can neglect this second term. The centrifugal distortion coefficient D is neglected. In second term, D is centrifugal distortion coefficient, and in Raman spectroscopy, we can neglect this. So we find a simple expression for rotational energy Ej equal to Bj j plus 1. This expression for rotational energy can be obtained from the relation that kinetic energy is half mv square and rotational energy is half I omega square. In the formula of rotational energy, we replace m by I, mass by moment of inertia, and v by omega, linear velocity, is replaced by angular velocity omega. So rotational energy is half I omega square. If we multiply and divide by I, then it becomes I square omega square upon 2I, and I omega is angular momentum. If we write angular momentum by L, then this becomes L square upon 2I, and according to quantum theory, angular momentum L, which we write for I omega, it is j plus 1 into h cross. So if we write for angular momentum L as j plus 1 h cross, we can find the expression for rotational energy as Ej equal to Bjj plus 1. All the coefficient of Jj plus 1 is written as B. That expression was in units joule. We can convert this in units of wave number, centimeter inverse. So rotational energy now here is written as Bjj plus 1. B is some constant. J is quantum number associated with angular momentum. So it is angular momentum quantum number. And value of J are 0, 1, 2, 3, 4 and so on. Now transitions between these levels follow the formal selection rule. Delta J equal to 0 or plus minus 2 only. These are the selection rules for transitions between two rotational energy levels. Delta J, change in J can be 0 or plus 2 or minus 2. The fact that in Raman work the rotational quantum number changes by 2 units than 1 is connected with the symmetry of polarizability ellipsoid. For a linear molecule, it is evident that during end over end rotation, the ellipsoid presents the same appearance to an observer twice in every complete rotation. If we consider a polarizability ellipsoid and we take end over end rotation, then it gives same appearance 2 times in a complete rotation. So this delta J equal to plus minus 2 selection rule comes. Transition delta J equal to 0 is trivial since this represents no change in the molecular energy and hence it represents Rayleigh scattering only. If we define delta J as J upper minus J lower, delta J is change in J, rotational quantum number. Change in J is written as J upper minus J lower, then we can ignore the selection rule delta J equal to minus 2 since for rotational change the upper state quantum number must necessarily be greater than in the lower state. So for delta J equal to plus 2, with the energy levels of equation 2 we have delta ES. Delta E is change in energy. For this transition, when delta J is plus 2, then change in energy delta E is equal to EJ plus 2 minus EJ. So here we consider the transition from a level having rotational quantum number j plus 2 to a level having rotational quantum number j, so that delta j is plus 2. This change in energy delta E is E j plus 2 minus Ej, and we write delta E S. The spectral lines obtained by such transition is termed as S branch lines. For delta J equal to plus 2, we find S branch lines. So we write this change in energy delta E as delta E S. Delta E change in energy for S branch lines when delta J is plus 2. Ej is Bjj plus 1 in this equation 2, and Ej plus 2 is obtained by replacing J by J plus 2 in this relation. So Ej plus 2 minus Ej is this B j plus 2 j plus 3 minus B j j plus 1. It is equal to B j square plus 5j plus 6 minus B into j square plus j, and it is equal to B into 4j plus 6. Unit is centimeter inverse. So this change in energy is in units of wave number, where j is the rotational quantum number in the lower state. Thus, if the molecule gains rotational energy from the photon during collision, we have a series of S branch lines to the lower wave number of the exciting line, that are Stokes lines. While if molecule loses energy to the photon, the S branch lines appear on the high wave number side, that are anti-Stokes lines. The wave numbers of the corresponding spectral lines are given by wave number of spectral lines are written as nu S bar. S for S branch lines, nu bar is wave number. It is wave number of spectral lines obtained by such transitions. So nu S bar will be equal to nu Ex is for excitation, that means it is wave number of incident radiation. So nu S bar, wave number for S branch lines, is equal to nu Ex bar plus minus delta Es. Delta Es we have found equal to B into 4j plus 6. So nu S bar will be equal to nu Ex bar plus minus B 4j plus 6. Unit is centimeter inverse for wave number, where the positive sign refers to anti-Stokes lines and the negative to Stokes lines, and nu Ex bar is the wave number of exciting radiation, that is of incident radiation. The allowed transitions and the Raman spectrum arising are shown schematically in following figure. These are the allowed transitions shown in above figure, and from these allowed transitions we find the spectrum which is shown in lower figure. In above figure different energy levels are formed corresponding to J equal to, these are the values of J having values 0, 1, 2, 3, 4, 5, 6 up to 7. We see as value of J increases, rotational energy increases, and this difference between two energy levels also increases, which is shown in this figure. The difference between energy levels for J equal to 0 and 1 is smallest, and as J increases, this difference in energy levels increases continuously. Allowed transitions for delta J equal to 2 are shown here. This is the first transition from level of J equal to 2 to J equal to 0. Second transition is for J equal to 3 to J equal to 1 level. Other transition is from J equal to 4 to J equal to 2 level. So for this transition, delta J is minus 2. Delta J, difference in J is minus 2, and these are the transitions having delta J plus 2. These are the transitions from J equal to 0 to J equal to 2, so delta J is plus 2, or transition from J equal to 1 to J equal to 3, it also have delta J equal to plus 2, and so on. And this is the spectrum. In the center we have wave number of incident radiation nu Ex bar. On its left side we have Stokes lines arising from these transitions from J equal to 0 to J equal to plus 2. This spectral line is denoted by number 0. So this 0 is value of J, and it is the lower value of J. Lower value of J for two levels in between transition takes place. So for this transition, when transition takes place from J equal to 0 to J equal to 2, this is written in this diagram as 0. And for this transition, from this relation, if we put J equal to 0, then we find nu S bar equal to nu Ex bar plus 6b, put J equal to 0. So nu S bar is obtained as nu Ex bar plus minus 6b if we put J equal to 0. Nu S bar equal to nu Ex bar plus minus 6b. So we get these two lines. (6b) distance from this central line on left side and right side. These two lines are labeled as 0. Lower value of J is 0 for these two transitions, and this difference of this spectral line from central line is 6b, because nu s bar is nu ex bar plus minus 6b. Similarly, if we put j equal to 1 here, then for j equal to 1 we have nu s bar equal to nu ex bar plus minus 10b. Nu s bar equal to nu ex bar plus minus 10b. If we put j equal to 2, we get nu s bar equal to nu ex bar plus minus 14b. So we see that first line is obtained at distance 6b from center line. Second line for j equal to 1 is obtained at distance 10b from central line. Next line for j equal to 2 will be at distance 14b from central line. So first line is at distance 6b from central line, and the gap between next two lines is 4b. In this way, these Stokes lines and anti-Stokes lines are shown. In the center we have wave number of incident radiation, excitation radiation, having wave number nu ex bar. First line is obtained at distance 6b, and other lines have separation 4b from each other. So this is rotational spectra, pure rotational spectra for linear molecules. Now we consider pure rotational spectra for symmetric top molecules. For example of symmetric top molecule is CHCl3 chloroform molecule, which is shown in this figure. CHCl3. The polarizability ellipsoid for a typical symmetric top molecule, for example CHCl3 chloroform, is shown in this following figure. The chloroform molecule and its polarizability ellipsoid seen from across and along the symmetric axis. Symmetric axis is the line joining C and H. So this line CH is symmetric axis. If we look across this line, then polarizability ellipsoid is shown in this figure. It is in the form of ellipsoid. But if we look along this symmetric axis, along this CH axis as shown in this figure, CH axis is in this figure is perpendicular to this plane of paper, then the polarizability ellipsoid will be spherical. So if we see across the symmetric axis, that is CH axis, then it is in the form of ellipsoid. And if we see perpendicular to the symmetric axis, CH axis, as shown in this figure, then it is in the form of polarizability ellipsoid is in the form of spherical shape. Plainly, rotation about the top axis produces no changes in the polarizability, but end over end rotation will produce such a change. We have energy levels. Now energy levels are written by this formula: E jk equal to B j plus 1 plus A minus B into k square. First term is similar to the previous case. it is the rotational energy B J J plus 1, and now we have one another term, that is A minus B into K square. Here J is rotational quantum number 0, 1, 2, 3, 4, and K is also a quantum number having values from plus J to minus J with a difference of 1. So if J equal to 0, then K is 0. If J equal to 1, then K is between plus 1 and minus 1 with a difference of 1. So values of K will be plus 1, 0 and minus 1. If J is 2, then values of K are between plus 2 and minus 2, that are plus 2, plus 1, 0, minus 1, minus 2. So values of K are from plus J to minus J with a difference of 1. So these values are plus minus J minus 1, and so on up to 0. And the selection rules for Raman spectra are delta K is equal to 0 and delta J is now equal to 0 plus minus 1 plus minus 2, except for K equal to 0 states where delta J is plus minus 2 only. For K equal to 0, delta J is only plus minus 2. K is the rotational quantum number for axial rotation. So selection rule delta K equal to 0 implies that changes in the angular momentum about the top axis will not give rise to a Raman spectrum. Such rotations are Raman inactive. The restriction of delta J equal to plus minus 2 for K equal to 0 states means effectively that delta J cannot be plus minus 1 for transitions involving the ground state J equal to 0. Thus, for all J values other than 0, K also may be different from 0 and delta J equal to plus minus 1 transitions are allowed. Now, if we consider delta J equal to plus 1, we get R branch line, and if we have delta J equal to plus 2, we get S branch lines. If delta J is plus 1, then delta E will be equal to EJ plus 1 minus EJ. Transition is from J plus 1 to J level, then delta J is plus 1. EJ plus 1 is BJ plus 1 into J plus 2, and EJ is BJJ plus 1. By solving this, we get delta E equal to 2B into J plus 1, and we write this difference in energy as delta E R for R branch line. That means for delta J equal to plus 1. So delta E for R branch line, delta ER is 2B into J plus 1. Unit is centimeter inverse in units of wave number, and here J is 1, 2, 3 and J is not equal to 0, because for J equal to 0, delta J equal to plus 1 transition is not allowed. So delta J equal to plus 1 for R branch line, values of J are from 1, 2, 3, 4 and it is not 0. For delta J equal to plus 2, we get S branch line as in the previous case, and this change in energy delta E for S branch line is EJ plus 2 minus EJ. EJ is BJJ plus 1 and EJ plus 2 is BJ plus 2 into J plus 3, and by solving this we get delta E for S branch line, delta ES equal to B into 4J plus 6. Thus we shall have two series of lines in the Raman spectra. And for R series, for R branch lines, we have wave number nu R bar equal to nu EX bar plus minus delta ER. Put the value of delta ER, that is 2b into j plus 1. We get nu R bar equal to nu EX bar plus minus 2b into j plus 1. Unit is centimeter inverse in terms of wave number. And for S branch lines, we have wave number nu S bar equal to nu EX bar plus minus delta ES. Put the value of delta ES, we get nu S bar equal to nu EX bar plus minus b into 4j plus 6 centimeter inverse. Here values of j are 0, 1, 2, 3, 4. And in the previous case, for R branch lines, values of j are 1, 2, 3, 4. It is not equal to 0. These R branch lines are shown in this figure. In the center, we have wave number of incident radiation nu EX bar. And on left and right side, we have these R branch lines starting for j equal to 1, 2, 3, 4, 5, 6. J equal to 0 is not allowed here. This difference can be obtained by using this formula nu R bar. We put the value of j here, put value of j as j equal to 1, then j equal to 2, then j equal to 3. These lines are obtained. In the second diagram, we have shown S branch lines. From this relation, nu S bar equal to nu EX bar plus minus b into 4j plus 6. Here we put the values of j as 0, 1, 2, 3, 4, and these different lines are obtained. Stokes lines on left side of this nu EX bar and anti-Stokes lines on right side of this nu EX bar. So in the first diagram, we have shown R branch lines, and in the second branch, we have shown S branch lines. And in the next diagram, we have shown the complete spectrum. In the center, we have wave number of incident radiation nu EX bar, and on left side of it, we have Stokes lines of R and S branch, and on right side we have anti-Stokes lines of R and S branch. Some R and S branch lines are coincide here.